Okay, so we're going to try calculating the probability with overlapping events. And again, this has another name. It's also called inclusive events. And in a minute, when we look at the Venn diagram, it'll be a little bit more obvious why we call these overlapping events. Also, the word inclusive is sort of the opposite of the mutually exclusive events. Mutually exclusive is different than inclusive. Now you'll notice that we're going to look at another example of rolling one die. And you might say to yourself, well, we just did that example and it was disjoint events, not overlapping. But notice how this is written out differently. In this case, we're going to try to figure out the probability of rolling one die and getting either a multiple of 2, sorry for the abbreviation, or a multiple of 3. So let's take a look. We're going to first start with the Venn diagram. And the Venn diagram, again, we start with a big old rectangle. Maybe that's even a little too big. And then we're going to go ahead and have a couple of circles. This time, our circles have some overlap. Now, before we start drawing anything in the circle, we're going to write what the circles represent. The first circle is going to be the event that you get a multiple of 2. And the second circle is going to represent the event that you get a multiple of 3. Okay, and so now we're going to take a look at, well, what do those events look like? What are the possible outcomes in each of those? Well, the thing is this. Multiples of 2 could be 2 and something else, and multiples of 3 could be 3 and something else, but it turns out that 6 is a multiple of 2 and a multiple of 3. So we throw that guy right in here in the overlapping region. And so what ends up oh, and by the way, I want to point out that this rectangle is still here to represent the rest of the universe, which is all the other outcomes that are not multiples of 2 or 3, and that includes a 1 and a 4 and a 5. And I think that's it. That gives us 6 possible outcomes. Okay, so we're going to go ahead and try to calculate this out. So let's go ahead and try to figure out the probability. Probability that you get a multiple of 2 looks to me like there's 2 ways to get that out of 6 total. That's a multiple of 2, so 2 out of 6. And again, I notice that this could be reduced, but I'm not reducing it just yet. The next thing we're going to do is we're going to add that to, because when we have an OR, we're going to add that to the probability of getting a multiple of 3. And we can see that there's 2 ways to get a 3, so again that's 2 out of 6. Coincidentally, these two probabilities are the same. So now there's only one little issue, is that if I stop right here, I'm going to get 4 out of 6. But the problem is that there's not 4 ways to get a multiple of 2 or a multiple of 3. There's only 1, 2, 3 ways. So what we have to do to fix this is we must subtract off the probability of getting both a multiple of 2 and a multiple of 3, and that is this guy right here. That is the number of ways you can get a multiple of 2. Let's see if I can write this. Multiple of 2 and a multiple of 3. Okay, this 6 represents multiple of 2 and multiple of 3, both. So we're going to subtract that guy off because that's overlapping. So there's 1 out of 6 ways to get a multiple of 2 and a multiple of 3. And that gets us our result of 4 minus 1, that's 3 out of 6. And again, finally, in the end, we can go ahead and reduce. But don't reduce until the end, and that means there's a 50-50 chance of getting a multiple. There's a 50% chance of getting a multiple of 2 or a multiple of 3 when we roll one die. Now, we're going to go ahead and try to formalize this using an algebraic formula. We're going to say if we're trying to figure out the probability of A or B, and we know that the events are overlapping or inclusive, then our new formula looks like this. We use the probability of A plus the probability of B, and we subtract off the probability of A and B, and if there is one, of course. And by the way, little trick for you here, little tip, is that this formula also works for disjoint events. It's just in disjoint events, the probability of A and B is always going to be 0 because you can never have both A and B occur in a disjoint event. So anyways, this formula is really very multi-purpose. Now, one last thing that I'd like to discuss is just using the Venn diagram. If we just use the Venn diagram, you can go directly to the idea that there's 1, 2, 3 ways to get a multiple of 2 or 3. And that's 3 ways out of 6. So again, right from the Venn diagram, we could have gone directly to the 3 out of 6 if we knew how to draw the Venn diagram. And again, we can reduce that to 1/2. And again, we can rewrite as a decimal or a percent. And remember that probabilities are always numbers between 0 and 1, including 0 and 1. And so they can always be written as a fraction, decimal, or percent. Okay, that's it. Oh, by the way, one last thing I will say is that the book does have some good examples with cards, and those you should probably look at those examples to get some extra ideas about how to calculate probability with disjoint events and also with overlapping events.